So today you're going to learn how you can actually price arithmetic Asian options on electricity futures. So we're going to be using the Australian electricity market and not the traded ASX average rate product, but we're actually going to be computing an over-the-counter bespoke product which is dependent on the average of the closing price of the futures in the contract period. Now we'll explain all that shortly. We're also going to be looking at how you can use variance reduction methods to get a more accurate Monte Carlo options price without increasing the complexity or the number of simulations in your calculation. We're going to look at a control variate, which is going to be the analytical solution for a geometric Asian option. So the geometric Asian option actually has a closed form solution, and we're going to use that as a good static hedge for our arithmetic option that we're trying to price. We're also going to look at what happens when we have a combination of antithetic and that control variate into our simulation and what benefits we get in terms of a reduction in the standard error around our option price and the computation time increase. So without further ado, let's jump into it. So again, we're using this risk-neutral pricing framework to be able to simulate risk-neutral asset paths in our Monte Carlo simulation so that we can get a fair price for our Asian option. So let's import the dependencies. Here we've got time, numpy, pandas, scipy, datetime, and matplotlib. Now for our path-dependent options, Asians, in this example, we're going to be pricing a European arithmetic Asian call option. So here, the option pays the difference between the arithmetic average of the price that we're going to call AT and the strike price K at maturity T. So the arithmetic average is taken as the setter's observations of the asset price STI, which follows a GBM at dates T1 through to N. So here, the Asian average price option has this arithmetic average of all the observed prices at these observable dates 1 through to N. So that means that here we have the payoff between our times where we're going to be having these average prices between T1 and T2. The payoff is going to be the max of this arithmetic average minus K. So here's our Asian call option. Sitting here at time T, we want to take the average between time 1 and time 2, and we want to take the risk-neutral expectation of this payoff discounted back to the current time when we're paid. So we're paid at time 2 and we're currently sitting here at time T. So this payoff here, CT between T1 and T2, is dependent on the forward prices that we're observing, our underlying between these two times. So here we're going to be considering the Australian electricity market, and we're going to be looking at average rate options for Q1 2023. Now in the national electricity market, the NEM, there are 5 separate markets for each state, and we're going to be valuing Q1 2023 electricity Asian options in the New South Wales market. So what we can see is that we've got the futures contract price for Q1 23. The last settled price was 135.89. Our current futures price for Q1 23 is the 135.89. Now our time currently is the 22nd of April 2020, and the actual period that we're going to be taking the average over is our Q1. So that's the starting time, T1, of the 1st of January 2023, and then an ending time, a maturity date, an expiry date, T2, which is the 31st of March 2023. Now this is a 90-day contract period. So for the actual ASX exchange product, which is the average rate option, what you're actually doing is you've got your average rate option that's settled on the end price of the futures contract. Now, the contract specification has an average taken over all of the wholesale prices, so it takes the arithmetic average of the wholesale prices, and that's how you settle against the futures contract. So this is an average taken on 288 trading intervals for each day over that contract period. So that's 90 days over 288 trading intervals per day, which leads to an arithmetic average on your wholesale price over 25,920 observations. So again, we get our current futures contract price for the Q1 23, which is settled at 135.89. Now for the Asian call price, we're going to be considering the strike that is being traded here at 165. So we've got 50 megs here that have been traded, and the previous close was $18.08. And that traded for an implied volatility of 53.07%. So that is the percentage volatility that we're going to be using here in this model. So our initial parameters are going to be the time, which is today, our start time for the averaging, which is the start of the contract period, and then we've got the expiry that will stop averaging over, so that's our end date, our T2. Then we've got the total amount of days over this contract period, 90. We have to add 1 because when we take the difference, we lose 1 day. And then we're going to initialize the parameters. So we've got our initial stock price, or our futures price. So we've got 135.89, which is the current price. We've got our strike price, which is 165. We've got the time to maturity, which is the difference between today and then the end average period, T2. We've got the annual risk-free rate, which we're calling 0. And we've got the volatility, which we've seen in the market, the implied volatility of that traded product, which is 53%. The number of time steps here is the 90 days times 288, which is the 25,920 observations. Now we're going to be simulating 1,000 prices. Now, in reality, it's really important, like I said, that this electricity average rate options in Australia and the New Zealand markets are actually settled against the final futures prices. So as futures are settled against the arithmetic average of the wholesale energy market price, the final futures prices, as you get to the end of the quarter, actually converges on the arithmetic average of the wholesale energy price. What does that mean? Well, that means that the reference price for the Asian style option exercise is actually in accordance with this final settlement price of the underlying futures. And it's determined on the 3rd business day after the final day of trading. So the method of option exercise is that at this time, if it's in the money, all Asian average rate options are actually automatically exercised into the underlying futures contracts and cash settled. Now, if they are not in the money and they're out of the money or at the money, then this transfer is not permitted. So what does this mean? Well, this means that options can be priced actually using the Black-Scholes until the end of the quarter. And we'll demonstrate that here. So here's our regular Black-Scholes pricing formula with our futures information. And here you can see that that was the traded price with those parameters, $18.08. Now, to actually make this more interesting and to actually demonstrate the price even of an average rate option, because some futures are not pegged to the arithmetic average like the Australian electricity market futures. So let's make this more interesting. Let's say that we're going to trade over the counter a bespoke average rate option over this Q1 23 period with the underlying as the same futures contract. Now let's say that the average rate option prices are actually determined by the average of the daily futures across the Q1 23 period. So what do I mean? I mean that we have now this OTC bespoke product that we're going to trade over the counter with someone else, where we've got our futures price today, and we're going to speculate what the futures price is into the future. So we'll use our Monte Carlo simulation, and we're going to take the arithmetic average across every day in the quarter of that futures price. And that's going to be used to calculate our Asian call option. So here's our slow step. We're actually going to step through things day by day. So now our N is not 25,920. Here it's just discretized every day. So we've got 90 days. So here we've got the time from now till time 2 is what we're going to call time T to T2. And from time T to T1 is the time before we actually start averaging. So the observed times is going to be our 90 days between time 1 and time 2. So these are called our observed starting times. We're actually going to append 0 to the start of this so that we can get a difference array so we can calculate the time between each one of our observation times. So here we're going to have 2 empty NumPy arrays, fulls of zeros, where we've got our new dt, so our drift term, and then our volatility squared with time. So here we're going to pre-compute the constants. So over this time period, we're going to calculate our respective constants. And the reason that they're not the same every period is because we're jumping from time 0 all the way to time 0.7 before actually taking the average. So hopefully that makes sense. We've got uneven time steps between our observation. We're going all the way from time 0 to time 0.7. So we're computing all our respective drift and then volatility terms between these time periods, our observations, which are then the same frequency every day in that 90-day period in a quarter. We've then got our Monte Carlo simulation, where at each Monte Carlo simulation I, we're initializing with our futures price today, and we've got our arithmetic sum that's initialized at 0. Then for all time periods, we're just going to simulate our epsilon, so our random normal, our Wiener process, and we're going to calculate our new futures price at that time step. So we just take the respective drift and then volatility term multiplied by our Wiener process. We can then add this to the arithmetic sum, and we continue doing this for the entire time of this particular simulation. Now at the end of time T2, so our 90-day period, we then take the arithmetic average, so we just divide that sum and divide it by n. So for the call price, we just take the max then of 0 and the difference between this arithmetic average and K. So here we're going to be using this sum of CT, so we can store our the total sum of all the CT variables, and we'll use that to calculate the expectation. We've also got the sum of CT squared, so we can be able to calculate the standard error. So we're going to compute the expectation, which is we just take over all of these Monte Carlo simulations, our 1,000, what is the average discounted expectation price of this arithmetic average rate option. And here we've got that it's $15.60 with a standard error of 1.3 with a computation time of 0.39. So now we're actually going to vectorize this. So we're going to use NumPy arrays to make it a little bit cleaner. So exactly the same initialization over that 90-day period. Here we're actually going to have our NumPy arrays actually indexed in terms of n, which is the time steps, and then m as well, which is our simulations. So our drift and volatility coefficients for each time period is going to be the exact same for each simulation. So that's why we're indexing by I for the time, but then keeping it the same for the simulation. Then for the Monte Carlo method, we've got this random normal of size by the number of time steps by the number of simulations. So here we've got an array of our deterministic plus our diffusion multiplied by this Wiener process for each respective time period at each simulation. So this is our changes in the stock price over time. And what we need to do is then we just need to take the cumulative prod of all of these exponential changes across each path. So we're taking the cumulative prod of these exponential terms across each simulation path and multiplying by S0. This means that when we index by our final time point at each of the simulations, we get in the final stock price outcome or futures price outcome. Now to calculate the average across all of these simulation paths, we're going to use not cum prod but cum sum. So now we're taking the cumulative sum across all these price paths on axis equals 0, and then we're dividing by n so that the final index point is the arithmetic sum. So now for all our simulations, we can use the NumPy maximum between 0 and then our final index time arithmetic average minus k. We can then compute the discounted expectation of this payoff and then the standard error. So as you can see, we've got 15.8 with a standard error, same as before, it's just been computed faster at 0.008. So now we're going to be looking at ways that we can actually complete variance reduction techniques on this Monte Carlo simulation. So the first one I'm going to look at is the antithetic variance reduction technique. So here we've got our fast simulation, but in our Monte Carlo method, here we're pricing the complete version of a negatively correlated variable. So here you can see that the diffusion component, we have the case where what happens if the future price was completely simulated as the negative correlation. So we're decreasing the complexity again and the computation time because we've already simulated the outcome of this Wiener process, but we're using it again and imagining a perfectly negatively correlated product. So we simulate these for every simulation, for every 1,000 simulations, and remember it's kind of like 2 for the price of 1. So what we're doing here is we're reducing our variance by only simulating the same number of random variables. So then we compute the prices along all the paths. So again, we just take the cumulative prod for these two different cases, and then we take the arithmetic average for these two different cases by using NumPy cum sum. Then we just take the average between these two payoffs, so just 0.5 times the maximum of the first arithmetic average minus this k, and then the plus the NumPy maximum between 0 and then the arithmetic average of the second case minus k. Then we compute this antithetic discounted expectation of these prices, and then we get a call value which is similar, 15.909, but we get a reduction in our standard error down from 1.3 to 0.86. So every time we run this simulation, we're getting an improved accuracy around our call value. Now, one of the best ways is to actually use a control variate, and one of the control variates we can use is a geometric Asian option. So obviously there's no analytical solution for the arithmetic Asian option. However, there is for the geometric Asian option, and this is because the geometric Asian option is the average of a product of normally distributed variables, and therefore itself is log normally distributed. So for a geometric average price, we've got this GT, which is the product of all of these prices across this time to the power of 1 over n. So this is the geometric average over this series of prices. So the payoff at maturity is again going to be priced the exact same way, except we're going to be substituting that arithmetic average for the geometric average. Now, this has a closed form solution because essentially we can rearrange the Black-Scholes formula to incorporate this aspect that the geometric average is the product of log normally distributed prices, which is log normally distributed. So we get this closed form solution of this price here. Now, this is for the discrete monitoring case where we're actually monitoring at discrete times, not continuously monitoring. And that's important because the option that we're pricing has discrete monitoring for the closing price of the futures at every day in that contract period. So here for all of these variables, n, there's an n number of observations to form the average, h is the observation frequency, and j is the number of observations that are passed, and in our case that's 0. So we can program that up and we can call a function that's discrete geometric Asian, where we're actually passing all of our conditions for the n, h, and j, and then computing our geometric discrete Asian option price. And here you can see that's about 15.95 for our case scenario here. So our tactic now for our control variate is actually not going to be for a delta control variate. So like we've done in the past, we're actually going to compute a portfolio. Now the portfolio is going to be the difference between the arithmetic and the geometric Asian option. So this is a very good static hedge for the arithmetic option, and instead of actually computing the delta at each time period, which would be increased computation, we're going to simulate this portfolio that's long the arithmetic option and short the geometric Asian option. Then at the end, when we've computed the discounted expectation of the price, all we need to do is add back on the analytical solution of the geometric Asian option price to our Monte Carlo portfolio simulation. So let's get into it. We price exactly the same way. So now we're calculating GT, which is just the geometric average. So we're taking the cumulative product of all these stock prices along each path to the power of 1 over n. And again, we're going to index by the final time period. So here is our portfolio. We've got our arithmetic option minus our geometric option payoff. And we're doing that for 1,000 Monte Carlo simulations. Here we take the discounted expectation of this portfolio payoff, and then we add back on the discrete geometric Asian price. So now what you'll see is that our call value is around the same now as 16.25, but our standard error has been incredibly reduced from 0.8 all the way down to 0.02. So an incredible reduction in the standard error. So now we're going to look at the antithetic and the control variate of the geometric average option and see how that helps in terms of variance reduction for our Monte Carlo technique. So now we're simulating, we're pre-computing the constants just as we have done before. For our Monte Carlo simulation, we have two price paths which are negatively correlated with each other. So that's the antithetic component here. So we've got two price paths, 1 and 2, and we're computing the arithmetic average for each of those prices, and we're computing the geometric average for both of those price paths for each of the 1,000 simulations. So then we're going to calculate our portfolio payoff. So we're going to take the average between the two portfolios. Remember, each portfolio holds it's long an arithmetic option and short the geometric option. And then it's got two price paths, 1 and 2. So we're just taking the average between those two portfolios. Now we're going to calculate the discounted expectation of this portfolio payoff over all these 1,000 simulations, and then we can compute our standard error, and then we add back our discrete geometric Asian price to this portfolio. And now we've got a very accurate price of 16.27 with a standard error of 0.02. Now the computation time has gone up. So let's compare these variance reduction methods and the computation time that it's taken, because again, you know, we've decreased the standard error, but we've increased the relative computation time. So just for an idea of what the slow estimate took, so here are all our Asian call option value prices on the left-hand side. Here we've got the standard errors that have been reduced as we've introduced these measures. So we've used the fast estimate, so our vectorized array, to benchmark our variance reduction methods. And we did this because this is a fairer comparison as these have been vectorized. So just so you know that if you do not vectorize it, it's about 50 times slower to run our for loops for all the time periods and for all those simulations. So much better to use NumPy arrays for this. As we move to the antithetic variate, what you get is a reduction in your standard error by about 1.5 for a relative computation time of 1.25 multiple. So the geometric control variate is where you see very significant gains for a relative time computation of only 1.4. So just a little bit more than doing the antithetic variate, you can actually get a 56 magnitude decrease in your standard error. And that's because the geometric average option is such a good price indication of your arithmetic average option. So it's a very, very good static hedge. Therefore, we get very significant gains in terms of this reduction in the standard error. Now, obviously you can see the benefit when then you add the antithetic variate with the geometric control variate. You get this further increased reduction of a multiple of 66, but that does take an increased computation time of 2 times just what our normal vectorized estimation was. So again, just to summarize, we took our own interpretation of an over-the-counter bespoke energy traded product, which was the average of the futures contract over the time period of that quarter, and we took the average of the closing price of the futures each day. So we used Monte Carlo simulation to be able to get the forward prices, our futures prices between those periods, and take the average over those price paths and compute the Asian call payoffs. And then we actually used a variety of variance reduction techniques to be able to get a more accurate price over this Asian option. So hopefully you learned a lot, and I look forward to seeing you in the next episode.